In the last segment, we looked at a correlation for determining the convective heat transfer coefficient across a tube bundle. And you recall we had a Reynolds number that was evaluated based on the diameter and a thing called Umax. So what we're going to do in this segment is figure out how to determine that maximum velocity. Now, in determining Umax going through a tube bundle, it's going to depend upon the configuration that we have. So what we're going to do, we're going to begin with the simpler, and that is for the inline arrangement. So let's assume that we have this configuration here where we have 3 cylinders, inline arrangement. The spacing between tubes is Sn. In the direction normal to the flow. We have free stream coming from the left to the right, and so the free stream velocity is at U infinity. And if you go back and look at the flow visualization from the first segment of this lecture, you'll notice that there's fairly significant jetting going on, or accelerated flow between the tubes, and we had this region of high velocity in the middle there. That is what we are going to refer to as being Umax for the inline configuration. So what we want to be able to do is, this is where we have the lowest area. Oops, sorry about that. The lowest area, and consequently that is where we will have the maximum velocity. So what we want to be able to do is evaluate the velocity at that plane, basically the point between the 2 cylinders. And so the way that we're going to go about evaluating Umax for the inline configuration is we're going to rely on fluid mechanics and the continuity equation. So if you recall from your fluid mechanics courses, continuity, here we would look at the mass flow coming in. And what I'm going to do is I am going to look at a section of flow that extends out in this direction. And so on the inlet, what we would have, let me erase those, that and that. And on the inlet, what we would have is we would have this here. And these are all at U free stream. So coming in, what we have is the density multiplied by the free stream velocity. Sn is our spacing, and we're going to assume unit width. And that is going to be equal to the mass flux coming through this region here where we have the constriction. So again, it is going to be the density of the fluid multiplied by this new maximum velocity. We do not know what that is yet. And the size of that opening, we can compute that from Sn as well as knowing the diameter of our cylinders. And so what we have here on this side, we have d over 2. That would be this distance. And then here we have another d over 2. That would be that distance. So I'm looking at half of the cylinder. So what we can say is that we have Sn minus d over 2 minus d over 2, which just turns out to be Sn minus d. We can now do some rearranging. First of all, density is going to cancel from the left and the right-hand side. And what I want to do, I want to evaluate this so that I can isolate Umax, because that's what we are interested in. So we then obtain an expression for Umax is equal to the free stream velocity multiplied by Sn divided by Sn minus d. And that is the way that we can evaluate Umax when we have the inline arrangement. The next thing that we want to do, let's consider the case that is slightly more complicated, where we have a staggered tube bundle. Okay, so there is our staggered tube bundle. What I want to do is I want to put the dimensions on here. So you recall from the first segment in this lecture, we talked about the direction parallel to the flow. That was SP, or the spacing in that direction. And we also talked about spacing normal to the flow. That was SN. And again, like before, we will have D as being the diameter of each of our cylinders. And what we are now going to have, again, we have U infinity out here. And if you go back and review the video for when we had the staggered tube bundle, you'll find that the flow comes along and it goes through a fairly severe change in direction. And so what is happening, we have two locations where we could say that we have a fairly significant constriction in space between the two bundles. One of them would be what we just saw, where we called Umax. That was for when we had the inline tube bundle, but I'm going to call this U1 because at this point we don't know if that is the maximum velocity or not. And then another location where we have a constriction is, although in this particular drawing it may not look like a constriction, but if you go back and watch the video, you will see that between these two tubes here, we have velocity going in this direction, and I'm going to call that U2. And one of those two is the one that would give us the maximum velocity. And what we're going to do, we're going to again use geometry and continuity and come up with an expression for U1 and U2, and whichever one is larger, that would be Umax that we would use in our Reynolds number. So what we're going to do, we want to find which is greater, U1 or U2. And we know from the analysis with the inline arrangement, we've been able to determine what U1 is. So that was the expression for U1. So that one we can put off to the side. And now what we want to do, we want to work on U2 and determine what it is. So let's take a look at determining U2. And looking back at our diagram, we notice that Sn, which we have here, is the distance from this center to that center. And so if we look at the distance from this tube center, that distance there is going to be Sn divided by 2. So we will use this in our drawing here. And then in the direction of the flow, or parallel to the flow direction, we know that this is Sp. So what we have here, we can construct a right angle triangle right here. And with that, we can write the following. And I am going to solve for L. So we now have an expression for L, which is telling us the distance from center to center of our tubes that are in the tube bundle. And just like before, what we'll be able to do, we know that this distance here is d over 2, and this is d over 2 as well, going from the center line to the surface of the tube, and so we will be able to correct for that. We're now going to apply the continuity equation, and what I am going to do is I am going to say U infinity was up here. Looking back at our larger picture, what we're doing is we're zooming in on this section of the flow here. So we're looking at that to there. So we're making the assumption that a streamline coming along here, it would hit a stagnation point on that cylinder. So half of the flow needs to go this way and half is going to go up that way. And that's how we're able to do this and apply it at Sn over 2. So with that, on the inlet side, we will be looking at rho u infinity Sn divided by 2. And on the right-hand side, that is going to be equal to rho u2, which we don't know yet, L minus d, because I'm minusing d over 2. I'll put it out explicitly. So we're doing minus d over 2 minus d over 2. And so with that, we can go through canceling out the density and rearranging our terms. We end up with the following expression. Okay, so we obtain that for U2, a little bit more complex than what we saw for U1. But what we can do, we can come up with a method, and essentially what we can say is the following. So if this condition is met, then what we can say is that Umax equals U1, and if that condition is met, therefore Umax is equal to U2. And all I'm doing here is I'm taking the term that is multiplying U infinity and comparing it. So that term, or looking back, this term. So I'm taking those and doing a comparison between them, seeing which is greater, and that enables us to determine Umax. And once you have Umax, once you have that, then you can evaluate Reynolds number based on diameter at the max velocity, which is required in order to determine the convective heat transfer coefficient within the tube bundle. So that is the way that we determine Umax in the tube bundle.